This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 8 of Week 4. Fans, blowers, and compressors. The machines that move gas instead of liquid. We classify them by pressure rise. Treat fans and blowers as incompressible, where the pump equations carry straight over. Run the fan laws, then cross into compressible territory for compressor work. And finish with why we stage compression and cool between stages. What separates a fan from a blower from a compressor is the pressure rise. A fan adds less than 3.5 inches of water column, ventilation. A blower 3.5 to 40 inches, pneumatic conveying, combustion air. A compressor, above 40, real gas compression and refrigeration. What matters is the physics, not the labels. When the pressure ratio is within a few percent of 1, density barely changes and the flow is incompressible. Fans and most blowers live there. Compressors do not, and that changes which equations you reach for. Fans reuse the pump machinery. Because the density change across a fan is negligible, the air behaves like an incompressible fluid, so the same hydraulic power form applies. Fan power equals volume flow times the static pressure rise over the fan efficiency. Flow in cubic feet per minute or cubic meters per second. Delta P is the static rise, efficiency typically 50 to 80%. That numerator, Q times delta P, is exactly gamma QH rewritten. Pressure rise times volume flow is power. It only looks different because fan curves are published in inches of water, not feet of air. And fan total pressure is static plus velocity. Use whichever the problem hands you. The fan laws. Not new physics, just the affinity laws applied to a fan. Change the speed, and 3 things scale by fixed powers. Flow scales linearly, pressure rise with speed squared, power with speed cubed. That cube is the whole story. Raise speed 20%, and power doesn't rise 20%. It jumps by 1.2 cubed, about 73%. That's why variable frequency drives save so much energy versus throttling with a damper. These speed-only forms assume fixed diameter and density, the usual exam setup. Let's work it. A ventilation fan is measured at 600 RPM, delivering 8,000 CFM against 1.5 inches of water static, drawing 4 horsepower. Now speed the same fan up to 750 RPM, same air, and find the new flow, pressure rise, and power. The plan? Get the speed ratio, apply the 3 fan laws, and notice how steeply the power term climbs. Apply each law with the ratio 1.25. Flow is linear, giving 10,000 CFM. Pressure goes as speed squared, so 1.5 inches becomes about 2.3. Power goes as speed cubed, so 4 horsepower becomes about 7.8. A 25% speed increase bought 25% more flow, but nearly doubled the power. The entire energy argument for variable speed fan control, and why an oversized fan, run fast, quietly wastes power. Compressors, where the air fights back. Once the pressure ratio is large enough that density changes meaningfully, the incompressible shortcut is gone, and you use thermodynamic work. 2 cases bracket reality. Isothermal, gas held at constant temperature, takes mass flow times R times temperature times the natural log of the pressure ratio. Isentropic, adiabatic and reversible, takes more, carrying the pressure ratio raised to gamma minus 1 over gamma, over the compressor efficiency. The shift is conceptual. Work now depends on the pressure ratio and inlet temperature, not on a head length. Always use absolute temperature and pressure. And isothermal is the floor, while adiabatic is higher, because the gas heats as you squeeze it. Put numbers on it. Air enters at 0.5 kilogram per second and 300 Kelvin. Compressed isentropically from 100 to 400 kilopascals, a pressure ratio of 4. Specific heat 1.005, gamma 1.4, efficiency 80%. The pressure ratio to the 0.286 power gives a bracket of 0.49, and the isentropic work formula lands at roughly 92 kilowatts. A pressure ratio of just 4 already demands about 92 kilowatts. Push it higher, and both the work and the exit temperature climb quickly. That rising exit temperature sets up the next slide. Why we stage compression and cool between stages. For a large overall pressure ratio, doing it in one shot drives the gas very hot, and that heat inflates the work. The fix is to split the rise into stages with an intercooler between them, cooling the gas before the next stage. A single adiabatic stage rides the high curve. Multi-stage with intercooling hugs the lower isothermal curve, the minimum work path. You also win a lower peak temperature, protecting seals, valves, and lubricant. The optimum, for N stages, minimum work comes when every stage handles the same pressure ratio, the nth root of the overall. For the exam, the why matters more than the arithmetic. Cooling toward isothermal means less work. The picture behind the idea. On a pressure volume diagram, compression work is the area to the left of the path. The adiabatic path, gas heating as it goes, bows right and sweeps a larger area. The isothermal path, held cool, stays tighter. Multi-stage with intercooling steps between them. Each cooled restart drops back toward the isothermal line. The shaded gap is the work intercooling recovers, real shaft power, often 10 to 15% on a large compressor train. 4 traps on the boundary between incompressible and compressible. 1. Using gamma QH on a real compressor. That form only holds when density barely changes, fans and low blowers. For a meaningful pressure ratio, switch to thermodynamic work. 2. Forgetting the cube on fan power. Flow scales linearly with speed, but power with the cube, so a 25% speed rise nearly doubles power. 3. Gauge instead of absolute in compressor work. The pressure ratio and inlet temperature must both be absolute, temperature in Kelvin or Rankine. 4. Confusing static, velocity, and total pressure on a fan. Power is flow times pressure rise. So use the pressure the problem specifies, and don't pair a static rating with a total pressure demand. Bookmark the pages. The classification table and the fan power equation, which is just gamma QH in disguise. The fan laws, the same affinity laws as pumps, with the all-important cube on power. And the compressible flow relations underpinning compressor work, both the isothermal and isentropic forms, plus the multi-stage intercooling idea. The two you'll reach for almost every time are the fan laws and the isentropic compressor work formula. You can now place any gas mover, classify it by pressure rise, treat fans and blowers with the incompressible flow times pressure rise over efficiency form, and scale them with the fan laws, flow linear, pressure squared, power cubed. The instant the pressure ratio makes density matter, switch to thermodynamic compressor work in absolute units. In Topic 9, we leave single machines for whole systems, pipes in series and parallel, the 3-reservoir junction, and the Hardy cross-loop method. The continuity and energy balance habits carry straight in. Flow conserves at every junction. Head loss balances around every loop.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.